So let's talk about algorithms in general. So this session, we want to understand why are we playing this card game? Well, this card game mimics exactly how computers sort information. So computers store information in an array. An array is a list, and so, for example, these numbers, if we want to sort them, we need to have space to be able to move our number and not lose our data. So typically what we would do, I'll just point. Okay, so typically what we would have is we'd have free spaces in the memory, and we have our list of numbers. And if we want to, for example, move the number 8 to the beginning, we can't just move the 8 to the 24 and write over it. We have to first save this information by moving 24 to the free cell, copying 8 to this first position, and then moving 24 to where 8 was. So in order for us to sort, we actually need a little bit of free space to be able to move data around. The computer can only compare 2 items at a time. The computer is going to use the less than operator typically. And so when you ask, does this letter come before this? You're doing a less than comparison. So you can only compare 2 things at a time. You can move items to free cells in memory. And the computer is going to follow a set of instructions, which are known as an algorithm, in order to perform the task, which is to sort. What are examples of things that computers need to sort? Your file directories, your Google search results, databases, so forth. There's many things that computers will sort. How do computers sort? What are common algorithms? So the first method that some people learn is called selection sort. So in selection sort, the idea is you want to find the very first element and put that at the beginning of the list. And then go through the list again and find the next largest element, and then the next largest element, and build up the list as you go element by element. So this algorithm is a relatively simple one. You can write maybe 4 lines of code, and it will perform this operation. Unfortunately, it's slow for large lists. So there's something called order of notation. This algorithm is order of n squared operations. What that means is that if I have a certain list, if I double the length of the list, the amount of time it takes me to sort is not double, it's double squared. So it's now 4 times as long to sort. If I triple the length of the list, it's now 3 squared, or 9 times as long to sort. 10 times longer list, 100 times longer to sort. So this is bad. So imagine if I had a million elements to list to sort. This is now going to take 1,000,000 squared operations. So this is generally not a suitable thing for large lists. So the way that we can visualize a sorting algorithm is with this graph. So the horizontal axis shows the position in the list. So the left side of the graph is the very first object in the list. The right side of the graph is the very last object in the list. And then vertically, we represent the value of the element. So the smallest element is at the bottom, and then as you go up vertically, you get bigger and bigger items. In order for us to sort, what we want is a line that increases monotonically, meaning it increases in a specific direction. So as we increase our position in the list, the value is always getting bigger and bigger. So our goal is to get something that's a diagonal line that's going upwards. So the way that selection sort works is you find the smallest element one at a time. So what we do is we block off a certain region of space. And let's say that we've already put the smallest element in the first spot, the second smallest in the second spot, and we've built up to like 12 or 13 elements where this 13th element is the 13th smallest. The question is, what do we do next? Well, with the remainder of the list, we want to search through this entire list to find the next smallest element. Once we've found this next smallest element, we need to move it to this position in the list. And then we proceed along until we've sorted the list. So this is an animation of how this process goes. So over time, we just keep putting the next smallest element in the list, and we build up our list of larger and larger elements. So this is selection sort. Okay, so the second version of sorting. So this is insertion sort. So this is the algorithm that Neil was using. So you build the sorted list 1 element at a time by inserting a new element into the correct position in the list. So his variation, he did the insertion a little bit quicker, figuring out where it's supposed to go by searching using a binary method. So insertion sort overall, it's a simple algorithm. it is fast for very small lists. It's probably the fastest one if you have a list somewhere between, let's say, 3 elements and 15 or so elements. Generally the fastest. However, it's also order of n squared, so it's slow for large lists. So I have 10 times longer list, it's 100 times more time to sort. So again, we have this initially unsorted set of data, and what we're going to do now, instead of selection sort, which is you block it horizontally, insertion sort, you're going to block it vertically. And so the idea is I've built up this part of the list. This part of the list is already sorted. So this part is in order. And what I want to do now is I have this new element that I encounter. I have to figure out where does it go on the list. So I need to insert it at this spot. The insertion step, there are 2 different ways to do it. There's the slow way, which is, okay, I have this new element. I'm going to compare it with each one of these and see as soon as it's not less than, then I know that that's, or as soon as I see it's something that it's less than, I know that's where it goes. So that's basically going to take a long time. What Neil was describing is binary search. So I'm going to first look roughly in the middle of this list and see is it before or after. Then if it's after, I'm going to look in the middle of the remainder of the list and see is it before or after, and then look that way. And so I can find where it goes much faster by doing this binary search portion.
So it's the technique you use if you're trying to guess a number quickly.
Yes, so
And
I'm
so
thinking of,
say too big, too small.
yeah, I'm thinking of a number from 1 to 100, and you say 50, and then they say lower, and then you say 25, higher, 37, lower, and that way you can get to the number very quickly, rather than saying, is it 1, higher, is it 2, higher, then 3, higher. That's going to take you a really long time. So you want to guess in the middle and then go up and down based on that. Okay, so we want to insert this new element in the list. So we know that it goes in this position. So for us to insert this object here, we need to move all of these objects over by 1 and insert that in. So we move it over 1 and insert. So the animation goes horizontally, so we keep picking up new elements and inserting them into the list. This part of the list is sorted, this part is unsorted.
Almost like a sweep.
Say it again?
It's almost like a sweeper.
It's like a sweeper.
Yeah,
you
you slide and you just keep, you sweep up and insert where
they go.
yes.
Yeah, so also compare it to selection sort. So in selection sort, it also, this is also sweeping, but it seems like it's moving. It's sweeping up. Yeah.
This one is doing this.
Left to right. Yeah.
Okay.
So that's the difference between those 2 algorithms.
Okay.
All right. So bubble sort. So sometimes this is the algorithm that people think of if they haven't done computer science before. Obama famously, I forgot where he went. I think it was at Google. And they asked him a technical question, and his reply was, well, I know I'm not going to use bubble sort. So bubble sort is like the pun of every bad computer science joke. So this is a very simple, but it's very slow for both small lists and for large lists. And so the method is you pass through the list, comparing adjacent neighbors, and you swap them if needed. You keep going down the list, swapping, and then once you get to the end, you go back to the beginning and go through the list, swapping one at a time. So what happens is that the large elements, they plummet to the back of the list very quickly because every time you go through, they keep pushing the way down. The smaller elements slowly bubble up to the top. That's how it gets its name. So in bubble sort, it looks like this. So in a single step, the biggest element gets put in the right spot, and each one of the elements that are too small, they only move 1 point for every iteration. So I go through this entire list making my comparisons of swaps. Once I've made it all the way through the list, this object has moved 1 space. So it bubbles very, very slowly. But the large objects plummet. Again, this is order n squared. So again, 10 times longer list, 100 times longer to sort. Okay, so what are strategies that are more efficient than this order n squared? So the problem with sorting large lists is that they're large, right? So let's think about how we can sort smaller lists and use the results of sorting smaller lists to improve the overall sorting algorithm. So one approach is called merge sort. This is known as a divide and conquer strategy. So I'm going to divide the problem, which is a very difficult problem, sort 2 billion objects. Well, I don't know how to sort 2 billion objects. I know how to sort 1 billion objects, and I know how to sort another 1 billion objects, and I'm going to merge those 2 things together. How do I sort 1 billion objects? I have to sort 500 million, 500 million. And I keep going through that process, dividing up the list smaller and smaller. So the approach is you divide the group in half, you sort each half, and then you merge the results together. The key part of this algorithm is that second step. How am I going to sort half of the list?
Merge sort.
You're going to use merge sort again. So I'm going to take that half of the list, I'm going to cut that in half, sort the left half, sort the right half, merge it together. Well, how do I sort the left half of the left half? Cut that in half. Sort the left, 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 sort the left, left, right. Merge it together. So this algorithm is very fast for large lists. It's order n log n. What that means is that if I have something that, let's say, is 1 million elements, so that's 10 to the power 6, if I compare that to something that's 10 elements, okay, I should have picked better numbers in my head. Okay, so 1 million elements versus, let's say, 1 element. N log n would be 10 to the 6 times log of 10 to the 6, which is about 12 or so. So it's about 12 million steps instead of 1 million squared steps. So you can see that's a huge improvement. So n log n is going to win versus n squared when you have a large number of lists. N is the number of elements in your list. It's also very easy to parallelize. And this is a very important thing for modern computing. So parallelization means that you're going to assign a task to many different processors on your computer. Yeah, parallel processing. Oh, okay. So with merge sort, what you say is, okay, I have this huge list to sort. I'm going to divide it up into chunks. And each one of the processors is going to sort one chunk. And this processor is just going to do that task. And once each processor is done, then I'm going to merge it together. And so a lot of the effort is in the sorting of these smaller lists. So it's slow, unfortunately, for small lists. And the reason it's slow is that this algorithm requires a lot of overhead. You have to have extra space to be able to store this information and divide up the problem. It also has lots of instructions. And so it's generally slow for small lists. And I mentioned that the simple version requires extra space. So let's look at this algorithm. So we divide the list in half, we sort the left half, we sort the right half, and we merge. So what does merge mean? Merge means that we're going to take these two half-sorted lists, and I'm going to figure out, does this one or this one come first? And I'm just going to go through and just compare until, and I'll keep going, like if these are all smaller, I'll keep going, and I'll start merging these things together.
So first and the first, and then the one that
Yeah.
comes second, you have to
So
compare to the other second?
So what you do is, let's say you have the two lists that are sorted. So you're going to compare the first elements in both lists. And whichever one wins, that one you put in the sorted list. And now, whatever list that came from, that's now the second element. Now you think of it as just the first element again. So now you're going to compare that to what's left in the other
Because
side.
we compare the one that didn't win to the second element and the three that did win.
Yeah, so once one list's elements has won, you move that into its place, because you know it comes before everything else in that other list. And once you've moved that over, now you have the rest of the list which is sorted, and you have to just see, okay, well, the second place in list A, how does that compare to first place in list B? And then let's say list A wins again. So now you move that second element over, and now you're comparing the third place in list A to the first place in list B. And then let's say a bunch of elements in list B start winning. Then you start putting those over, and maybe you compare the third place with the 10th place in the other list. So you go through merging elements.
Now, you said I did the bubble. I did 4 up here and 4 down there,
Okay.
and then I did this, and then I did that.
And then did you compare the two?
Yeah.
Okay, so so now I understand your algorithm a little bit better. So you did merge sort for just part of the process. So you're merging at the level of 4, and you're switching to a simpler algorithm for when you have a small number of elements. Yeah. So that's another very important strategy. Understanding that merge sort is slow when you have small lists compared to something like insertion sort. So divide the list up into a small enough chunk that you can use one of the faster algorithms to do that small chunk. So Again, we divide the list in half, sort the left half, sort the right half. The way we sort the left half is we divide that in half. We sort the left, the left, right, merge that together. Okay, so now we're ready to talk about quicksort. So you'll notice that quicksort has many steps in it. So quicksort is arguably, most people won't argue this, most people will just say yes it is, the fastest sorting algorithm for computers. And the reason it's fast is that it utilizes some of the features in the way that the computer stores information in memory. It uses what's called locality of reference, which means that if I'm looking at what the value is of a certain part in the memory, and I want to know what the value is right next to it, that operation is relatively quick. If I want to move objects and I move them around, the way that quicksort moves things around, it minimizes sort of the amount of data that I need to move. Okay, so the process. You pick a card that's called the pivot. So you pick something that you think is somewhere in the middle of the list. The goal is to divide the list by putting cards to the left that are smaller than the pivot, things that are greater to the right of the pivot. So you do this a lot when you alphabetize. You say, okay, A through K, you're on the left side, L through Z, you're on the right side. And then when you go to the left side, then there's another subdivision that says A through G, you're in the left half, and then H through K, you're in the left right half. And so then you sort that way. So it's very similar to that. So, but the way that they do it is you want to move through the list in an efficient manner. So I'm going to illustrate this on the board. So you start on the left side. So let's say the pivot is somewhere in the middle. I start moving on the left side until I find something that's on the wrong side of the list. So these first elements are supposed to be on this side. So I leave them where they are. I found something that's in the wrong position. I start on this side, I start moving in until I find something that's in the wrong position. So this object should really be on that side, this object should be on that side. So then what I do is I copy this to memory, I move this over, I copy this one back. And so that's switch these two. So now this part of the list is on the correct side, and I keep moving down this side of the list until I find something that's in the wrong side. I move down this list until I find something on the wrong side, and then I swap them. I keep going that until I get to the middle. When I get to the middle, I put the thing that I'm comparing to in that spot. And now I know everything on this side is less than that object, everything on this side is greater than that object. So I split the list in half, roughly. Everything's smaller, everything's greater. Now I can sort just this half list, and I can sort this half list. So this is another divide and conquer strategy. This one is called partition and exchange. So I'm partitioning the list, and I'm exchanging to get things onto the right side. So this is fast for large lists. I mentioned this is the fastest for practical computing. In the average case, it's also n log n. So it's very similar to merge sort and how much it scales. However, if you pick very bad pivots, it can be n squared. So if the first time I pick the object, it's actually the first element in the list, then I'm going through this list, and all I get is, okay, everything's to the right of it. And then I pick the second element accidentally, and I put everything to the right of it. So then that becomes n squared. It's not very common that that'll happen, but you just have to be aware that sometimes quicksort can be slow. It's generally slow for small lists, and the reason is that there's a lot of steps and a lot of overhead. So the process, let's say this is the pivot. So I'm going to move everything, so I'm going to go through the list, move everything less than the pivot to this half, everything greater than the pivot to this half. I'm going to look at this half list, find a pivot, move everything to the left of that, everything to the right of that. This half of the list eventually will get sorted. Then I'm going to go over to this list. I pick this as the pivot, I move everything to the left that's smaller than that, everything to the right that's greater than that. And I keep picking pivots until I get a sorted list. So that's the process for quicksort. Okay, let's talk about a really bad algorithm. So the bad algorithm I want to talk about is called Bogosort. So in Bogosort, what you do is you check to see, is it in the correct order? So I just randomly flip over whatever order it happens to be in. Is this in the right order? And you're going to say no. And so if it's not, you throw the cards up in the air, you cache them, you rearrange them, you've now shuffled the cards, and they come out in a different order, and you look and you ask, is this now in the right order? And the answer is no. So you throw them up again, cache them, is this in the right order? No. So you can imagine how long this is going to take, right? So this algorithm will take n factorial steps. So if I have 5 objects, 120 steps.
Yeah.
6 objects, 720 steps. Actually, it's n times n factorial over 2. But it scales so badly that you never want to do this. So why do computer scientists want to study something like bogus sort? Like, what is the practical value in studying an algorithm that's really, really bad?
Does it have to do with like chance, like how many times will this number come up or something like that?
Yeah, so you can use it to understand certain probabilistic things.
Probability.
You can look at probability and the odds that, let's say, you pick something at random and you get like, I don't know, you're gambling and you're picking the first, second, and third place horse races, the odds that you'll get it correctly. It will scale like n factorial. What are other examples? Yeah.
Would it be for comparison's sake, so you could be able to say this method is 10 times better than the dumbest method possible?
Yeah, you can do that sort of comparison. You can basically say the worst possible case, it's not that much worse than that, or not that much better than that. Yeah.
Are you actually displacing chance versus method?
Okay, so this
Or
one,
chance is your constant, because it's always a chance, like, you know, and from there you're developing actual methods.
mhm. Yeah. So there are things, so people do study things where you have randomness in your process. So you mentioned actually earlier that sometimes the oracle gives you the wrong answer.
Right.
So if there's a chance that the oracle gives you the wrong answer, being able to understand how to make algorithms that are robust against that error is important. So actually, I'm going to take off a tangent on that topic. So sports, the playoff system. So most sports have a best of 7 playoffs, right? NBA, well not NFL, but NBA, hockey, baseball, they do best of 7. And the reason is they want to ensure high probability that the better team wins. Now the strategy that they have in terms of brackets and so forth, like the winner, like 8 versus 1, and then the winner of that plays 2 and so forth, that's designed to maximize the chance that the best team wins the tournament. So you want to figure out how to sort those 8 teams that made the playoffs, or 16 teams that made the playoffs, and figure out who's the best team. And the tournament system is designed to minimize sort of the number of comparisons. The number of comparisons are like the games that you've played, but still have high probability that the best team wins. Now there are many different playoff systems. So in tennis, there's something called a ladder system. Does anyone here play tennis? So in ladder system, like you play against, you have the option to challenge the person who's ahead of you on the ladder. And if you win, you move up the ladder. If you lose, you move down the ladder. So in that system, the goal is to figure out who's the best player in ranking. And so they do comparisons one at a time. Does that sound like any of the algorithms we study? So it's like the first 2 players play, the winner moves on. The second 2 players play, the winner moves on. And you go down the list until you find the best player. So what algorithm does that sound like? Bubble sort, yes. So the tennis ladder is very similar to bubble sort, where the best player will eventually bubble up to the top. There are other algorithms such as round robin. So round robin, basically every team plays every other team. So that algorithm actually has the best, or has the highest, or the most likely to pick the best team when there's the chance that sometimes there's upsets. So round robin, where it's regular season and whoever wins the most games, that's actually shown mathematically to be the best way to find the top team. So a lot of people argue, should we have a playoff system? Should it all be based on the regular season? As a computer scientist, you'd say it should be regular season based and you shouldn't have playoffs because there's too much chance. Yeah.
Big tournaments, well, for scholastic ball, 8 or 10 member tournaments, that's usually what I run.
Round robin, yeah.
What are they doing in chess?
In chess.
Yeah, because like if you go to like
First board, second board.
they
I don't know the
no, they,
tournament
like in
structure.
chess they'll do like they take your rating, right?
Mhm.
And you only play people within a certain amount of rating, but it can be somebody who's 800 points higher than you. Okay, so then you could have somebody who plays a 500 level play a 1200 level player, or whatever. And then you have 4 people you play in that day, and then based on that, then you can, like your ranking can go up.
Mhm.
So, or change, and like, you could lose one, but you still could be in the, to win because you beat somebody who was a higher level player.
So
What is that?
it's a little bit like the ladder system in tennis. So you're playing people who are very closely ranked, but it sounds like there's some
They'll play
range.
people who are- yeah,
There's
they're
some
higher,
range in
yeah.
terms of how much they can
And you
move.
could get somebody who's,
Mhm.
you could get like 3 people who are close to you, and then you could get somebody who's
Very far
18
away.
Yeah. very
So
far
it's a
away.
little bit like bubble sort, but you have the option of not just comparing nearest neighbors, but you're comparing people who are further away on the list. So, okay, so coming back to the original question, so Boger sort. So the reason that some people study Boger sort is because problems tend to map onto each other. There's certain types of problems that you can say are analogous to other types of problems. So let's say you're solving some problem in medicine, or you're solving some problem in design, and you figure out that what you're doing is equivalent to Boger sort. You're just checking to see, does this work? It doesn't work? Let me try something else. Does this work? Try something else. If you're doing that, then clearly you should be thinking about how long it's going to take you to find the right answer. And you may be able to map your problem into a way that you can figure out how to solve it using a more sophisticated algorithm such as quicksort or merge sort or one of these other types of problems.